Okay, so we're going to assume, we can easily assume, specific heat is constant at a temperature within our operating temperature range. What does that mean? Well, that means, I've got to restart my timer. Okay. So when that timer goes off, I'm really going to have to stop. Okay, so what does this mean, Steve? Again, the integral of C sub v as a function of temperature with respect to temperature is equal to delta U. So that means I need C sub v as a function of temperature. Well, it's going to be, again, a third-order polynomial. But over small temperature change, if you can approximate this as a linear function, meaning it's going to be a constant slope. C sub v is just going to be C sub v t. And so you can just, or C sub v delta t, and you can just pull that constant slope, or this constant specific heat out of the integral. So if we assume the specific heat is constant, it comes out of the integral. I'm just integrating dt. Integral dt is just delta t. So what we normally do, now this is for ideal gases. For ideal gases, we'll say that delta U, which is equal to the integral of C sub v dt from T1 to T2. And what we'll normally do is we'll say, well, let's approximate this as C sub v at the average temperature multiplied by the change in temperature. And that'll give us a really good approximation for delta U. And I can do the same thing for H's. I can say delta H, the change in enthalpy, which we'll need in Chapter 5 when we talk about control volumes. There's a special case in Chapter 4 when we deal with constant pressure where this becomes important. We can talk about that. This is equal to the integral from T1 to T2 of C sub p dt. And what we can do is we can approximate that if I assume that the C sub p is a constant value at the average temperature. It comes out of the integral. And then I'm just integrating dt. Well, that's just delta t. This is a common thing that we will do. I do need to go get a good C sub p or C sub b average value. If I don't know both temperatures, it is going to involve a guess and check iteration. We'll probably see that later in the course. Okay, what else? Example. Okay. So we work an example here. I've got a rigid tank contains 20-pound mass of air at 50 psi and 80 degrees Fahrenheit. The air is heated until the pressure doubles. Determine the volume of the tank and the amount of heat transfer. This is L9, page 5. Got an example. So, again, what are we looking for? We want to find the heat transfer. That's what the problem statement says. Find, let me put this over here where we can see it. Find the heat transfer. I've got a tank. Again, what are we looking for? We're looking for Q. What do we know? We know the mass, 20-pound mass. Before I go too far, I should remind us that this is air, A-I-R, just air like we would breathe. We wouldn't breathe this. It's at a much higher pressure. P1, it looks like it's going to change. Yeah, they said the pressure is going to double. So initially it's 50 pounds per square inch absolute. That's what the A there stands for. It's pounds per square inch, and that's absolute. The initial temperature, 80 degrees Fahrenheit. The air is heated until the pressure doubles. P2 is equal to P1, so that's why it's important that this is an absolute pressure, because we're going to double that. Determine the volume of the tank. Oh, so two things. Determine the volume of the tank and the amount of heat transfer. Now there's one thing given here that I have not written down. Does anybody see it? Pause it. Take a look at the problem statement and see if there's something here that I've forgotten to write down. Go ahead and pause. Okay, so what did I forget? What does this adjective mean? Anytime you see an adjective describing your system or an adjective describing a process, you need to know what does that adjective mean. The term rigid is important. There are two generic types of systems we will see in Chapter 4. You will see a rigid, constant volume situation, or you might see a piston cylinder. That's kind of a nice generic system where the volume can change. So that's kind of the two main things. You always need to know, is my volume changing or not? Because if the volume is changing, what do we have to do if the volume's changing? Pause it. If you don't know this answer, you need to pause it. Go look. What do you do if you know the volume's changing? You need to compute something. So pause. Okay, so now you know what you need to do if the volume's changing. Okay, that's important, by the way. But since the volume's not changing, we don't have to worry about that here. Let's find the heat transfer. Yes, Izzy, we're recording videos. My cat is talking to us. I apologize. We'll probably have to let her in here in a second. Okay, trying to find the heat and the volume. Now, what is a good tool we could use to find either one of these? Well, I think we could find the volume. I mean, a lot of times when I ask students, okay, in the class, how would we find the volume? And the first response would be table properties. Okay, well, if you go look at the table properties for air, for an ideal gas, you don't have specific volumes like you do with water in R134. You've got a reduced volume, which you could use for something else later, okay? Yes, Izzy, we're recording. Thank you for checking on us. Come here. Say hi. Everybody say hi to Izzy. Okay. Yes, we're doing just fine. Thank you for checking on us. Okay, so if we're trying to find volume, right? Volume is a property. What do we know about our substance? Well, it's air, right? If we treat that air as an ideal gas, I know pressure and temperature at state 1. I know the mass. I can go find R. Volume's my only unknown. So that one's pretty easy. Okay? And the volume's constant. V1 is equal to V2. So I have to find two different volumes. Just find one volume, and that's the same. Okay? So that one's going to be easy. What is a good tool I might have to find the heat transfer? Okay, seriously, at this point, well, okay, it might be a little bit early in the class, but in the very near future, when I ask you, how do we find an unknown heat transfer or unknown any kind of energy, it needs to be a gag reflex, first law. First law is always the first thing we'll try to use to try to find an unknown energy. All right, so how do we write a first law equation? Well, the first thing you do is you draw your system. All right, first thing you do is you draw your system. Remember that the first law, you like my system there? It's an awesome system, right? Remember the first law always tells us that in minus out equals change, right? What crosses the boundary? What energy crosses the boundary? Because we need to know what energy comes in and goes out. Heat, right? It's being heated. As the problem statement said, it's being heated. So heat comes in. Is there anything applying a force to this that's going to do work? Any electricity? Is the volume changing? Those are kind of the three questions you want to ask about, is there work being done? Is there a work term? There's nothing applying a force. There's no volume change. There's no electricity. Those are kind of common ways you would see work being done here. I don't see any of those. So the only thing coming in is going to be heat. And if I'm looking for the heat in, I'm probably not going to worry about the heat out. Let's just assume we're looking for the heat net in. So in minus out just simplifies down to Q. You can write the big long equation and cross the things out that you don't want. That's fine. Or you can just draw your system, just like you would in a statics or physics class. Draw your free body diagram. Draw everything that's attached to it. In those classes, that's forces. Here we're talking about energy. So draw your system. Draw the energies crossing the boundary. That is your entire left-hand side of the equation. Add the ends, subtract the outs. Here I just have heat in, so that's my entire left-hand side of the equation. It's a stationary system, so the only energy that's going to change is going to be the internal energy. There's my first law equation. By the way, if this is a test problem, I would probably, if this was a 25-point test problem and I'm doing it in class, I'm going to put 10 points on getting this equation correct, 5 points for showing me you're also going to use this to find that. So you're at 15 out of 25 points. You're essentially passing at this point, and you can do that very quickly. You want to be able to write this equation correctly, quickly. Practice, practice, practice. Draw your system, draw the energies, add the ends, subtract the outs, equals the change. Done. Okay? I didn't have to go look at a solutions manual or a website to figure that out. You shouldn't either. You might up front, but you really need to get to where you don't. Okay? What do we know? We're looking for heat. We know the mass. I don't know the U's. So how do we find U's? Well, we go back and say, all right, well, what are some ways I can find U's? I could probably use table properties for an ideal gas. I do have an ideal gas. Or I could use specific heats. Let's try the specific heats. I know delta U, we can approximate a C sub V average delta T. Okay, let's do that. So let's say that this is approximately M C sub V at the average temperature times T2 minus T1. C sub V gives us delta U. All right. So now I need a couple of properties. The fact that it's air is really all I need to go find the R value. So I need R value in English units. Let's see, which ones do I... Just to mention, in your text, now if you're joining us from another course and you're not using our text, I don't know if your text gives you these same R values that ours does. Ours is really nice. In the English tables, they give you, this is table A1 in the English set, they give you an R value here, and not only the traditional energy per mass per temperature, they also give you R in pressure times volume per mass per temperature, which is, these are the same quantities, right? These are the same quantities, but sometimes you need these units, sometimes you need those units. It's easy to convert BTUs to pound force feet, and then convert pound force feet to pounds force per square inch times cubic feet. That's doable, but that's already done for you in our text. I don't know if your text does it. Again, if you're a guest, I don't know if your text gives you this value, but ours does. For air, R is 0.3704 psia cubic feet per pound mass per Rankine. Two different R's. They mean different things. This is temperature. This is a constant. Okay? All right. Yeah, Izzy, we're okay. Thank you, though. All right. So now, Steve, why did you get this one and not the BTUs per pound mass Rankine? We'll look at the units here. This is going to be PSI. This is going to be cubic feet. This is going to be in Rankines. So I need something here that's in PSIA cubic feet Rankines. Again, you could use the BTUs per pound mass Rankine. You're just going to have to do some conversions to use it. All right, what about C sub V? So that's going to give me this R to give me the volume. Down here, I know the mass, I know the temperatures, or at least I can find. Ooh, I don't know both temperatures. Ew. How do I find T2? So that's a property. So the first thing, when I'm trying to find a property, the first thing I want to do is say, okay, what is my substance? What are some ways I can find properties for that substance? So what is my substance? It's an ideal gas. Okay, so what are some ways I can find, it's air, it's an ideal gas. So what are some ways I can find properties for an ideal gas? Well, ideal gas law. So P1, V1 is equal to M R T1. And what I like to do with the ideal gas law when I'm going between states is move all of my variables to one side. So pressure and temperature can vary. Move my variables to one side, put my constants on the other. So mass does not vary, R does not vary, and the volume does not vary. And what I can do is I can set that equal to the other states. In this case, I've just got state 2. So I need T2. So T2 is going to be, oh, I got to quit right there.